范院长，我们开始了啊。
好的。
Dear colleagues, good afternoon and good morning to the colleagues from China. Good afternoon for the colleagues from Europe, and welcome to the Symposium of Frontiers in Cancer Science. I'm Dr. Baiyong. This is a privilege and great. First of all, allow me to introduce you the distinguished guests from 3 countries. The first, my dear friend, Professor Fan Xianqun, who is the Vice President of Jiao University and the Chancellor of the Jiao University School of Medicine.
OK， 尊敬的
And Professor 谢谢范校长，我介绍一下他们这其他几个，然后请您 OK。And the Professor Pr Yongbing, le président de Cancéropôle, Lyon, Auvergne-Rhône-Alpes. And the Professor Graham Lord, the Vice President, University of Manchester. Professor Robert Bristol, Director of Manchester Cancer Research Center, Chief Academic Office at the Crystal NHS Foundation Trust, and also Professor Véronique Trillet-Lenoir, the Professeur d'Oncologie, membre de Européen Parlement. Well, as you know, that this symposium will focus on 4 topics: the epidemiological research on tumor, new technology for the tumor screening, the diagnosis and treatment, cancer and chronic disease management. And first of all, I would like to invite the Professor Fan Xianqun to give us a speech. 范院长，
谢谢，非常感谢沈伯庸先生，尊敬的格莱罕罗德院长，尊敬的罗伯特布里斯托主席，皮埃尔埃诺主席，维罗尼克特里耶莱诺尔教授，以及各位来宾、同事们，大家好。
Thank you very much, Professor Shen Baiyong, Distinguished Dean Graham Lord, Director Robert Bristol, President Pierre Arnaud, Professor Véronique Trillet-Lenoir. Dear colleagues, ladies and gentlemen, good morning and good afternoon.
本次肿瘤前沿学术交流会首次由上海交通大学医学院与曼彻斯特大学生物医学与健康学院和法国奥罗尔大区里昂癌症研究中心共同举办。我很荣幸能够代表上海交通大学医学院欢迎来自国内外的各位专家。
This is the first time that we hold a trilateral symposium on frontiers in cancer research, together with the Faculty of Biology, Medicine and Health, University of Manchester, and CLARA. It is my great honor, on behalf of Shanghai Jiao University School of Medicine, to welcome all the distinguished guests from home and abroad.
上海交通大学医学院前身是由圣约翰大学医学院、震旦大学医学院和同德医学院于1952年合并建成上海第2医学院。海纳百川，始终坚持国际化路径，是上海交通大学医学院的一贯的办学理念。目前已发展成为一所享有较高国际声誉及医教研以及社会服务全面发展的研究型、创新性的医学院校。
Shanghai Jiao University School of Medicine was formerly known as Shanghai Second Medical College, which was merged by St. John's University School of Medicine, Aurora University School of Medicine, and Tong Medical College in 1952. Since its establishment, it has been very much committed to international cooperation. Now it has become a research and innovation-oriented medical school with all-round development in clinical services, scientific research, and social services, with very high international acclaim.
上海交通大学医学院与英国、法国的交流合作历史悠久。临床医学法语班是我院 医学教育的一个特色。于1980年开始招收第一届学生，30多年来培养了800多位法语医学人才，成为国内外临床医学的或研究的中流砥柱。
Shanghai Jiao University School of Medicine boasts a long history of exchange and cooperation with France and UK. The clinical, medical, and medicine French class is one of the distinctive features of our medical education. The first batch of students of the French class were registered back in 1980. To now, it has trained over 800 medical professionals during the past 30 years. And it has become a very fine example of collaboration between China and France in producing healthcare professionals.
自2014年起，我院与法国里昂奥罗尔大区癌症研究中心开展合作，每年选派3到6名学生前往法国奥罗尔大区开展院校学习交流。自2018年起，中法双方每年轮流举办肿瘤学术交流会议。
In 2014, the School of Medicine of Shanghai Jiao Tong University established cooperation with CLARA, and since then sent 3 to 6 students to the French partner universities each year with the support from CLARA. Since 2018, our medical school and CLARA have been taking turns to hold cancer research symposiums.
上海交通大学医学院与英国曼彻斯特大学的校际合作始于2017年，至今已举办双边论坛4次，合作发表论文38篇。我们之间的交流合作源远流长。此次更集肿瘤前沿学术会议之机，汇集双方专家，希能将科研合作推向新的台阶，书写医学科研领域新的篇章。
The official cooperation of the School of Medicine of Jiao Tong University with the University of Manchester began in 2017, and since then, the two universities have been keeping constant exchanges and cooperations. By now, the two universities have held 4 bilateral symposiums and jointly produced 38 papers based on our symposiums. To leverage our time by gathering experts from 3 countries, push international scientific research and cooperation to a new height and to write a new chapter in the medical scientific research.
肿瘤是全人类健康共同的威胁，肿瘤防治是上海交通大学医学院的重点研究方向之一。本次肿瘤前沿学术交流会聚焦肿瘤前沿研究，分设4个专题，分别从多组学与人工智能的肿瘤研究、肿瘤筛查与诊疗新技术、肿瘤与慢病管理、肿瘤的流行病学研究4个方面，探讨肿瘤学的研究、预防和治疗。
Cancer is one of the most common threats to human health, and cancer research on prevention and treatment is one of the priorities of our School of Medicine. This year, the Symposium on Frontier in Cancer Research will explore the latest research and development on prevention and control and treatment of cancers through 4 topics, namely epidemiological research on tumors, cancer and chronic disease management, the path of tumor research in the multi-omics and AI era, and new technologies for tumor screening, diagnosis, and treatment.
疫情当前，线上会议是一个很好的方式。学术交流唯有开放合作，群策群力，方能致远。衷心祝愿双方专家通过本次论坛深化肿瘤领域科研合作，通过科技创新共同探索解决重要的全球性的问题的途径和方法，携手共建人类卫生健康共同体，共同守护人类健康美好的未来。预祝本次论坛圆满成功，谢谢。
Today, the COVID-19 pandemic is still ravaging the whole world. Virtual meeting online is a very good approach for us to collaborate. It is of great importance to stay open and pour the wisdom of all parties. I sincerely hope that all experts will will come up with profound ideas to push the scientific cooperation in cancer science broader and further, and to find better solutions to resolve global challenges through scientific innovations. Together, we aim to build a community of common health for mankind and jointly protect the future of humanity.
I have to go. Is that work scientist work? Is that work
好
that
的，
you
谢
can...
谢，谢谢范校长。
谢谢。
Thank you very much, the fan. And now I would like to invite Professor Pr Yongbing, le président de CLARA, the president of Cancéropôle, Lyon, Auvergne-Rhône-Alpes, to deliver the address. Pierre.
Dear colleagues from Shanghai and from Manchester, it is a great pleasure to welcome you in this meeting and to stress the importance that this meeting is taking over the years in the relationships, strong relationships that we have built with the CLARA, with the research community of Shanghai, through this wonderful collaboration that has been going on now for a number of years. You are in Shanghai, a fantastic research university with amazing developments over the past 15, 20 years. And we are extremely proud to have the opportunity to develop this long-lasting collaboration with you. It is also wonderful to welcome the colleagues from Manchester into this initiative and to develop this meeting jointly with you on this occasion. We are, of course, very sorry that the meetings cannot be held in presence. Hosting you here in Rhône-Alpes region, in Lyon, and going to Shanghai have been a really great experience for all of us, and in particular for all our younger scientists and researchers who could accompany in these trips and really make strong contacts that have led to important collaborations, as you have just underlined. CLARA is a small organization. It's a structure that coordinates research in region Auvergne-Rhône-Alpes. And it's a big scientific region. There are 4 universities, 4 university hospitals, 1 center for clinical center for cancer research of international standing. The community regroups over 2,000 researchers dedicated to cancer research, to all aspects of cancer research, basic research, clinical research, all aspects of translational research, and also strong line of research in social sciences and in cancer prevention. Among the remarkable components of this community, there is the International Agency for Research on Cancer from IARC WHO, whom some of the scientists will intervene in the meeting over the coming days. This type of international collaboration is really a great opportunity for sharing and for developing long-term exchanges. It is important to keep this line of collaboration open over years so that we can really work on building something, as it has been done through students and many students from Tong University who have come to us for masters and PhD programs. It is important to keep it going when travel is restricted, like in these times of pandemics. So we really welcome the possibility to continue developing these great exchanges through support like Zoom today. So I wish all of you and all the participants an excellent meeting, and I'm looking forward for the beautiful programs and talks that have been put together on this occasion.
Thank you very much, Professor Yongbing. Thank you, Pierre. As Professor Eno has mentioned, that we have held this conference, Symposium of Cancerous Research for a couple of years. And since this year, we have a new friend, new participant from England. Now, I would like to invite Professor Graham Lord, Vice President, University of Manchester, to give us an address. Please.
Thank you. And good morning to friends and colleagues in China. Good morning to new friends and colleagues in Lyon. It's great to meet you, Professor Jianchun Fang, for the first time, and also Professor Eno. It's a great pleasure to meet both of you. And this is a real pleasure for me to send greetings from Manchester to all of our colleagues across the world. I'm so pleased to see the continued development of the collaboration between Manchester and Shanghai, even through the difficult times of the pandemic. And as Professor Jianchun Fang said, we've managed to learn new ways of working during the COVID pandemic. And I'm sure we will capture the best of those working practices as we seek to build on our new and existing collaborations. This collaboration with Manchester and Shanghai Jiao started in 2017 with Chancellor Chen, and has developed through 3 symposia, 2 of which were in person and 1 was virtual. And I'm delighted to sign and renew our Memorandum of Understanding with Shanghai that I signed recently as part of our Chinese Scholarship Council Innovation Platform application. And I very much hope for a successful outcome for this CSC Innovation Platform application. A positive result from that application will really boost the collaborations between all of our universities by providing the much needed research staff who clearly do all the work and drive the collaborations that lead us to treat cancer and other diseases more effectively. I would particularly like to thank Catherine Dye, Helen Lee and Annette Barber for their hard work on completing the CSC Innovation Platform application, and also for preparing the new MOU that I signed, and also for their help with planning this symposium. And looking through the programme, it looks like a very exciting series of talks and collaboration, and I look forward to seeing the outcome of these collaborations in new findings, new papers, and also new partnerships. I wish everyone success with this fantastic symposium, and I really hope that the joint research talks will help us to identify new collaborations that can be supported by the CSC Innovation Platform. I'm delighted how the symposium has the potential to link 3-way collaborations now between Manchester, your long-time partners Lyon, and Shanghai, and forge links between countries across the world. I think what COVID-19 and cancer shows us is that diseases don't particularly sit in any one country. They're not bounded by national borders. They are universal problems of humankind that we're all here to solve. And I think it's very, very important, particularly as been mentioned before, is that the UK continues to look outwards, and Manchester is very proud to continue that tradition. And I'd like to finish my opening remarks with an open invitation to all of you on this call to come to Manchester when travel allows, because it'd be very good to see you all face to face to discuss such brilliant science. So thank you very much. Welcome, and I'll hand back. Thank you.
Thank you, Professor Lord. And I really hope, as you wish, that this triangle symposium of cancerous research will be held routinely each year, every year.
Yes.
And now I would like to invite Professor Robert Bristow, Director of Manchester Cancer Research Centre, to give us a speech, please.
Thank you. It's an absolute pleasure to be here today, having attended the symposia previously and in person, being at Jiao in Shanghai. It's such a fantastic opportunity again to really synergize our scientific interest for the best impact on patients, and now to also be able to collaborate with CLARA and Lyon. I think this is a fantastic opportunity. I wanted to just take a few moments just to explain some of the assets within Manchester, and I think you will see not only today but throughout the week that there are a number of complementary scientific approaches across all 3 countries. Just to explain, the Manchester Cancer Research Centre is based on a partnership with the University of Manchester, our assets within Cancer Research UK programs, as well as the Christie Hospital, which is Europe's largest single-site cancer center. And so therefore, these resources come together such that we can drive NHS strategic goals, bring together a number of pieces regarding commercialization and innovation, and drive multidisciplinary science. So cancer is one of five research beacons at the University of Manchester, and our cancer center is akin to an NCI designated comprehensive cancer center in concept. We have a number of nodes of research excellence. This includes the Manchester Institute with CRUK, which is a driving basic discovery research institute, but also tumor site-specific centers of excellence, including prostate cancer, for breast cancer, as well as for lung cancer, and a very strong program to enact cell therapies and immunotherapy throughout our trusts. Importantly, we also have strong programs in biomarkers that you'll hear about a little bit later this week, as well as in radiotherapy. So these are our main strengths at the present time for our cancer center. So it includes informatics, but also early detection, experimental cancer medicine and early clinical trials, radiotherapy, including proton beam therapy and the use of MRI-LINAC, molecular pathology and integrated genomics, biomarkers, and immuno-oncology and cell therapies. We're a large program, so more than 240 million pounds in active research grants are within this research ecosystem, and we have more than 150,000 biospecimens collected across tumor sites, both trial-related and non-trial related, again for collaboration, and close to 5,000 patients per year are entering clinical studies, both phase 1 through to phase 3 within the program. Importantly, on the right, and I think this will be a strong component of the platform, of course, is empowering future leaders amongst ourselves as three partners. And currently we have approximately 200 trainees at the level of non-clinical and clinical PhDs right through to clinical fellows just prior to entering their oncology career. One of the areas we're very engaged in internationally is early detection. And so we are one of the 5 founding partners of the Cancer Alliance for Early Detection, internationally driven by CRUK. And our research areas include mobile prevention early detection units, understanding the genetics of risk, novel biomarkers with deep integration into early stage tumors, modeling effectiveness in health economics, and importantly, also taking ex vivo specimens of normal tissues from patients at risk and using bioreactors and advanced materials, try to understand genetic instability in those cultures. And we're very excited by a new building that is going up just now, shown on the right, be completed at the end of 2022, which will have a strong education hub and public education piece, but also co-locating our cancer scientists with our clinical health teams within the Christie Hospital, side by side, to drive new and innovative research programs within the Manchester setting. So we have strong, vibrant international research partners, and France and China now continue to be part of that strong alliance. And we really look forward this week to hearing about the granular details that will drive our joint ambitions. Please feel free to go onto our website to understand more about our research programming, again, to allow PI to PI interactions and to look at the breadth of collaborations between our 3 countries. And as Graham said, we welcome you to come and visit Manchester, which has just been ranked within the top 3 best cities in the world. And we'd love to show it off, not only the city, but of course also our science in collaboration. And I look forward to this week's meeting. Thank you.
Thank you, Professor Bristow. Thank you for your speech, and also thank you for your invitation as well. And now I would like to invite Professor Véronique Trillet-Lenoir, Professor of Oncology, member of European Parliament, who is a good friend and old friend of us, to give us a speech. Of course, she cannot join us online today, but she will address his wishes through a video recording. Let's welcome.
亲爱的同学们，亲爱的朋友们，我很高兴再次见到你们。 Cher Pr Baiyong, doyen de la faculté de médecine de Jiao Tong à Shanghai, cher Pr Hainaut, président du Cancéropôle Lyon Auvergne-Rhône-Alpes, chers collègues et chers amis, c'est un grand plaisir pour moi de présenter ce forum franco-chinois de cancérologie, avec le double regret de ne pas pouvoir être en direct avec vous, retenu par mes activités parlementaires européennes, et aussi le regret de ne pas pouvoir vous retrouver physiquement dans cette période difficile qui éloigne les amis. Nous avons toujours beaucoup de plaisir à nous retrouver à Shanghai ou sur les sites de notre région Auvergne-Rhône-Alpes, mais je sais qu'un jour, nous y arriverons. Nous allons échanger aujourd'hui sur de nouvelles technologies de diagnostic, de traitement et de prise en charge des patients atteints de cancer, dans un esprit de coopération constructive et amicale, celui qui nous anime depuis plusieurs années et qu'il est tellement important de conserver. Je suis heureuse que cette dynamique d'échange que nous avions mise en route se poursuive avec toujours autant d'énergie et autant d'ambition. Je compte sur vous pour que cette session 2021 soit aussi riche que les précédentes et je remercie toutes les équipes chinoises et les équipes françaises qui ont travaillé ensemble pour que ce nouvel événement se déroule de la meilleure façon et je formule tous mes vœux pour que vos discussions à ce forum soient intenses et fructueuses.
Merci beaucoup, Véronique. Right now, Véronique, she can speak very fluently Chinese, English, and French as well. And thank you all for coming and participate this program. And before we finish the opening session, I would like to remind you that there will be two sessions at the same time in the different Zoom link. Let's now take a few minutes the break and then pick up one you are interested in to join. See you in a few minutes. Thank you all. Thank you.
Dear everyone, I am Milena Nora. I am in charge of international relationships at CLARA Cancer Cluster, and I'm really glad to moderate this first session on epidemiological research dedicated to cancer. We'll have the pleasure to listen to 6 international experts from Shanghai, Manchester, and France. And just a little agenda reminder before starting. Each talk will last 20 minutes, and we'll have a question and answer session at the end of the session. So to begin this interesting session, I'm pleased to welcome Professor Pr Baiyong, Vice President of Regine Hospital, affiliated to Jiao Tong University, and also Director of Pancreatic. Professor, let's talk about diabetes and pancreatic cancer. The floor is yours.
Thank you very much, Milena. Thank you for your presentation. And I would like to report to you a recent research concerning the epidemiological oncology for city of Shanghai. As we know that the pancreatic cancer is his incidence is raising and become more and more pancreatic cancer in the countries of Europe, in China, Korea, Japan, and in North America as well. And we all know that the risk factor related to the pancreatic cancer, aging, food, and also the diabetes. But there is a very interesting phenomenon, which is the pancreatic cancer can also lead to the diabetes because the parenchyma of the pancreas involved by the tumor. So we have the less capability to secrete the insulin, so the diabetes appears. So what's the real relationship between the diabetes and the pancreatic cancer? So in this study, we try to answer the questions. The first is the absolute and the relative risk of a pancreatic cancer across different age and at onset. The second, the association of diabetes duration and the risk of pancreatic cancer. The third is the association of FBG levels and the risk of a pancreatic cancer. Of course, the third, the relationship between the BMI levels and the pancreatic cancer. And this study includes 42,000 population in the city of Shanghai, include diagnosed with the type 2 diabetes after 2011 to 2018. We followed this Shanghai, the population of Shanghai, for 8 years and aged 20 years or elder, and excluded the 206 type 2 diabetes patients in whom the pancreatic cancer was diagnosed 6 months before the confirmation of the type 2 diabetes, because we should exclude all the patients, all the diabetes caused by the pancreatic cancer. So we do the diagnosis of the diabetes prior to the pancreatic cancer 6 months before. And in this cohort study, we have totally 42,000 new onset patients with the type 2 diabetes. And these are the baseline characteristics of pancreatic cancer. In this cohort, you will see that in all these new onset pancreatic cancer, the age, the BMI, the FPG are the risk factors to the pancreatic cancer. And these are the incidence of the pancreatic cancer in general population of Shanghai in the cohort of new onset. So it is quite interesting because in our study, you will see that the absolute and the relative risk of a pancreatic cancer with the new onset type 2 diabetes patients across the different age groups. In each age groups, the diabetes patient have more raised incidence of the pancreatic cancer compared to the normal population. But which is the most interesting, you see in this group, the patient from 20 to 52 years old. That means for the young population, the diabetes patient has a more risk compared with the other age groups to get the pancreatic cancer. So although the incidence of pancreatic cancer increased with age, relative pancreatic cancer risk was inversely related to the age of the diabetes onset and a very higher SIR.
So I'm sorry, Professor, excuse me. There may be a problem with your presentation because we are still in the first slide. We are looking
you can see my slide?
Yes, but only the first one.
Oh, really?
We are on the PowerPoint, okay. But the presentation that is exposed.
Okay. You mean that my slide doesn't move on, just it stops in the first slide?
I think it's not the right mode to see the presentation. It's like you haven't started the diaporama.
Ok. Le diapo ne bouge pas, c'est ça?
Oui, en fait, on est sur le mode... je pense que vous avez partagé la présentation, mais vous partagez l'écran du PowerPoint et pas l'écran présentation.
Ok, mais je vais vérifier, je vais voir. Alors, bon, hop. Attends, je vais refaire.
Oui, je pense qu'il faut arrêter la diffusion et recommencer.
OK. Maintenant, ça bouge?
Non.
Pour l'instant, c'est toujours la même chose. Ah, ça y est, c'est bon. Parfait.
C'est bon? OK.
Perfect. Sorry.
Oh.
Ah.
Right now, it's
Perfect.
okay.
It's okay now. Thank
Fine.
you.
So sorry. Okay. Well, okay. Can you hear me clearly?
Clearly, it's okay.
Okay, fine. Well, I very rapidly, I'll repeat my first three diapo. The relationship between the diabetes and the pancreatic cancer. We all know up. Well, okay. And we try to answer these four questions after a investigation and the relative risk of pancreatic cancer across the different age and at onset of the diabetes. The second is the association of diabetes duration, and that the relationship between the duration of diabetes and the risk of the pancreatic cancer. The third is association of FBG levels and the risk of a pancreatic cancer. The fourth is the association of BMI levels and the risk of the pancreatic cancer. And in this study, totally 42,000 included diagnosed with the diabetes, the type 2, from 2011 to 2018. We follow these patients for 8 years and aged 20 years or elder. And we excluded too in these patients the diagnosis of the pancreatic cancer is prior to the diabetes. So we should eliminate the patient for that the diabetes is caused by the pancreatic cancer, because the parenchyma of the pancreas is involved by the tumor, so the patient get the diabetes. And so totally in this cohort study, we have 42,000 new onset patient with diabetes type 2. And these are the baselines of characteristic of patient of pancreatic cancer in this cohort. You'll see that the age, the BMI, and the FBG levels are the risk factors which is related to the pancreatic cancer. And very interesting, which is, first of all, that's regarding the age. The auto incidence of pancreatic cancer increased with age. A relative pancreatic cancer risk was inversely related to age of the diabetes, the type 2. In this group, that means the patient from the 20 to 42, and you see that the SIR is 5.72. That was observed in the age of young. Although in every age groups, the diabetes patient more risk to get a pancreatic cancer. In the a group of 75 from 50 patients. In very young patient is a very, and this is a similar male and a female analyzed separately. So this is the first information we get. The second is we were calculated the duration of the diabetes and the relationship with the duration of the diabetes and the pancreatic cancer. The absolute and relative risk of pancreatic cancer with diabetes type 2 across different diabetes duration group there was an inverted G-shaped curve. You see that between the risk of pancreatic cancer and the diabetes duration. So the new onset type 2 diabetes was significantly associated with elevated risk of pancreatic cancer in all 8 years follow-up, with a very high crude rate and SIR among the diabetes type 2 diagnosis within 1 year in this group. That means the diagnosis of the diabetes onset within 1 year, he has the most high risk to get the pancreatic cancer. Of course, within the 3 groups, that means the 6 years, 7 years, and more than 7 years. So in totally, the duration of the diabetes is related to the risk incidence of the pancreatic cancer. But very interesting, which is once the diagnosis of the diabetes onset within 1 year, it's the most high level. And a similar curve was seen in male and female analyzed separately. And concerning the FBG, the level of diabetes, you see that this group, this line is the FBG superior to 10 millimole per liter was associated with increased risk of a pancreatic cancer when we compared with the person get the FBG less than 6 millimole per liter. So the severity, if the diabetes is very severe, so at that time, otherwise the blood glucose is very poor controlled. In all these patients, they will have the most risky patients for the pancreatic cancer. And this association also can be seen in both sex. So we can give you some get-home message. The first is the young onset diabetes type 2 diabetes. The second is the long diabetes duration. The third is the poor glucose control. And these 3 factors might be important risk factor for pancreatic cancer. And this suggested that the efforts towards to an early and a close follow-up program, especially an individual with the young onset type 2 diabetes and the tighter glucose control might represent effective strategy for improved detecting and the result for treatment of a pancreatic cancer. And this is a very new, recent epidemiological research based on the population of Shanghai. Why we do this? Because the big city such as Shanghai, Tokyo, Lyon, London, because the population, they have the similar, the habitat of the lifestyle, the food style. So the diabetes is a risk factor. It is in our common knowledge. And the young population of once onset the diabetes, the type 2, it is a very high risk. And also the duration and the poor glucose control are also similar, the risk factors for the pancreatic cancer. And a little words about my center. The center is in Shanghai Regional Hospital, the Pancreatic Cancer Center. We have totally 126 beds. And these are the surgical procedure performed per year. For example, last year, each year, nearly 1,000 surgical procedure performed in this center for the pancreatic surgery. And this is my team. So our aim is to, the first is to prolong the survival rate of the pancreatic cancer. The second is because in my center, one big characteristic is the minimally invasive robotic pancreatic resection. Of course, in the institute, we try to analyze the mechanism of the pancreatic cancer and how to prove the long-term survival of the pancreatic cancer. It is a quite a difficult task. because we have done several things. The first is concerning the anastomosis of the pancreatic jejunostomy. We do a little bit different compared with the other surgical colleagues all over the world. So with that technique, the pancreatic leak fistula rate is 202.32%. Routinely, we have the pancreatic jejunostomy. The pancreatic fistula rate is about 60%. And this is reported the youngest pancreatic duodenectomy patient, 14 months, use that technique. And the second is we do something otherwise differently is the lymphadenectomy, because the lymph node spread is a characteristic of pancreatic lymphadenectomy. For that, we can have a more negative surgery margins for the head of the pancreas. For example, we do the extended lymphadenectomy for the lymph node group 14 and 16. For the body of the pancreas, we do also the lymphadenectomy for lymph node group number 9, and also for the distal pancreatectomy, and we should say that we should have at least 19 lymph nodes. And for the other, anyway, for the pancreatic surgery, extended lymphadenectomy within the courage therapy for the pancreatic cancer. And for the borderline tumor and local advanced tumor, after the new adjuvant chemotherapy, how we can do the resect of that tumors, we do remove the vessels and replace by artificial vessels. For example, this is the vein. We remove the vein by artificial levels, and this is the artery, SMA, superior mesenteric artery. We also remove the artery by a level. And for the late case, we do something after the chemotherapy. We do the combined vessel resection. That means we remove the pancreas and also the metastatic tumor in liver, in lung, in the other place. And for this group, we can have the 8.3% 3-year survival. So anyway, after the combined strategy of the treatment of the pancreatic cancer, and we have a 5-year survival overall till now in my group is 16.2%. And after radical resection, the 5-year survival for the pancreatic cancer is 27.5%. This is our recent report. Okay, thank you very much.
Thank you very much, Professor, for your nice talk. So I hope you will be connected at the end for the question and answer session to discuss with other participants. And now, thank you. I am pleased to welcome Professor Kenneth MUIR from the Division of Population Health, Health Services Research and Primary Care, School of Health Science and Faculty of Biology and Medicine and Health, who will talk about genes and lifestyle. So I welcome you to speak and to share your screen if you have a presentation, please.
Yes, Ni Men Hao, bonjour, many thanks. I shall share my screen now.
Sure. We can see you and we are waiting for the presentation.
Okay.
Perfect.
Yes, okay, so thank you very much for the opportunity to speak. What I thought I'd do in this short talk is remind us of some sort of older epidemiology and then take us through to some of the work that my colleagues and I are doing at Manchester, and welcome questions and would like to explore opportunities for collaboration. We're already working on quite a lot in Asia, and and enjoy working with colleagues around the world. So the plan for my talk was really to remind us of some older epidemiology results, because I think they set the scene of where we're going and they raise some of the challenges for modern epidemiology. I'd like to highlight the work that we're doing, which really looks at new results and tries to apply them, translate them into benefit. And this is often quite challenging. And then I'll say a little bit about our future plans and current direction, and like to explore that with the group. So my starting point really is ecological epidemiology, and this is some old data. And what it shows are the rates of prostate cancer around the world. And this is revealing in that the first take-home message is that cancers, different types of cancers show different prevalences with quite dramatic differences across populations. So for so-called Western countries, we see very high rates of many epithelial cancers, prostate, breast, colorectal. And traditionally, these cancers were rather rare in Asian countries and in the Caucasus. So already we get a hint that potentially something in the environment or the lifestyle of the people in these populations is influencing their cancer rate. We can break it down further, and if we look at the incidences of the top 3 or 4 cancers in each country, we see in, for example, Europe and the UK, we see high rates of prostate, breast and lung, colorectal. Okay, and in Asia, we see a different top 4 or top 5 of cancers. Now, that raises questions. Why is there a geographical difference? What are the causes? So, as you know, many of us have been studying multiple factors, lifestyle, diet, etc. And we will see, what the current challenges are, despite epidemiology and scientific endeavor for the past 40 or 50 years. Are we getting any nearer to knowing what causes cancer? This is another slide I like to show often. This is the 20 most common cancers in the UK. And as I say already, 4 of them dominate. So if we can make a public health difference to these top 4 cancers, we would be going some way to alleviating the cancer burden. This is another interesting slide, and this shows the change, age standardized rates across Europe of several cancers. And the point about this slide is that we see quite dramatic changes over a relatively short period. Down the bottom, we see that some cancers have decreased in incidence by maybe up to 1/3. And if we look at the top, some cancers have definitely increased in incidence. Some of this is artificial, maybe more surveillance, maybe more screening, but some of it is genuine and real. And therefore, we're seeing that cancer is a dynamic process influenced by the environment in which we're living. And epidemiology focuses on studying risk factors, and certainly the environment and the lifestyle remain important things to look at. If we look at the history of epidemiology, we know that we can make a difference, and the major success of epidemiology is smoking and lung cancer, but there have been several other successes. The point is that these classical success stories have really focused on what are large risk factors. And increasingly, as we go forward, the challenge is trying to look at smaller risk factors. And the implication of that is that we need very large studies. I'll say something about that. The second point is that there is definitely a genetic component to cancers. This is some general data across common cancers in the West, and we see the familial relative risk is always above 1 if there's cancer running in the family, and this familial relative risk, the FRR, is increased if the proband, the first cancer, is occurring less than 60. So we shouldn't rule out the important contribution of genetics to cancer. And predisposition is something that there's been a major effort to characterize here in Europe and increasingly across Asia and the other countries. This is another old slide, but I thought I'd show it for this audience because what it shows also is that there is a dramatic effect of the environment despite your genetic background. So let's just look at the top bar, if you like. Chinese people living in China have a very, very low rate of prostate cancer or other epithelial cancers. Chinese people that move to the US, suddenly within about 15 years, because they're adopting some of the lifestyle and some of the environmental factors, their rates do go up. So it's nothing in the Chinese genetic material that's inherently protecting them. The environment and their genetic background are no doubt coming together to influence the overall rates. So where does this leave us? So when I started epidemiology many moons ago, it was very much you were either an environmental epidemiologist or you were a geneticist. And there are examples of where the two causes of cancer do not interact very much. If you smoke, you will probably develop lung or other cancers. And if you have these high penetrance genes, BRCA, etc., then you'll probably be at very high risk of breast cancer and other cancers. Increasingly, though, I think the challenge is really looking at environment and genetic factors together. And one of the things that we've been trying to do over the past years is characterize the interaction between the environment and the genetic factors. And really, this hasn't been very successful. I'll make some comments on why I think that is the case. And it's really a sort of missed opportunity in a way. But I think there are implications for future work within that. So what are we currently doing here in Manchester? Well, we're focusing on gene-environment interactions, and we're doing work actually in Southeast Asia, looking at breast cancer. We are interested in taking the risk prediction information, be it from genetic or from epidemiological factors, and combining them together into combined risk prediction models. We are also using genetic risk prediction models on their own, and both these types of models, these prediction models, are increasingly being applied to improve screening procedures here in the West, but also we're starting to apply them for prevention studies. Can we target interventions at the higher risk groups, and how do we define the higher risk groups? And if we tell people they're in a high risk group, what do they make of it? So this is a very classic slide, just to bring to your attention that it's now well established. A number of SNPs, or single nucleotide polymorphisms, little tiny changes in the DNA code, have been identified, and we can now combine those codes, the predictive SNPs, and make a prediction of your breast cancer predisposition risk, your prostate cancer predisposition risk. We've been contributing to major international consortiums that have helped to establish approximately 300 markers that you can use in a combined genetic risk prediction model. And Gareth Evans will say a little bit more about breast cancer later. I'll introduce some of the work we're doing on prostate cancer now. So this is ultimately the holy grail. What I've done in this slide is represent really the hope of this. If ultimately we can find all of the genetic markers and all of the prediction factors and combine them, maybe we can identify a 20% subpopulation in which maybe 80% of the cancers occur, and in the remaining 20% of the population, in the remaining 80% of the population, only 20% of the cancers occur. We're not at this stage. There's a lot more work to be done, but we're moving towards that. So increasingly, we can stratify the underlying risk and target our work at the susceptible population, not forgetting that we need some provision for those at lower genetic risk. And that may be to remove them from the harms of some screening programs. So on my next slide, introduce something that may be bringing genetic and environmental factors together. And this is an increasing area of what we're doing here in Manchester. What we now know is that whereas the genetic code is fixed, the changes that occur in terms of methylation and aging that change chemically the way that the genes are expressed are very dynamic. So as we saw earlier, cancer incidence rates are changing, the environment is important, but that's working against a genetic background. And what we can show with epigenetics, and in particular methylation changes to the DNA, is just how things like physical activity, tobacco smoke, etc., actually imprint onto the DNA and change what the genes are expressed. If these genes are involved potentially as regulating repair processes or are directly involved in carcinogenesis, then they explain how the environment impacts, and they allow us to focus our studies much more than the broad epidemiological type studies of the past. So what are we doing with these types of risk prediction models that are based on genetic, environmental, lifestyle, diet, and increasingly using epigenetic markers? What we're doing is using these to educate the population. We run a test of real people, assess their risk at 3 levels, feed that information back to individuals, and see if that motivates them to make lifestyle change around the factors that we know are important. So currently we are profiling 600 to 800 people. We score their epidemiological risk, genetic, and their epigenetic risk. And over the past year, we've been trying to work out the appropriate messaging of this. And then what we will do is support people to make a lifestyle change, measure it through the epigenetics, and feed that back to individuals. This is focused around prevention of cancer. And we know that changing a lifestyle is very challenging, but if we inform people of their progress and their change in their biology, we feel that this might be helpful to them. What are the other things that we're doing? We're very interested in looking at changing what risk prediction models actually focus on. Typically, risk prediction models focus on, do you get cancer, yes or no? And what we know is that we need to refine that. And the relevant event might be death rather than whether you get cancer, or it might be an earlier stage of the cancer, and that's where we're trying to intervene. So that's where we should predict the risk. What we are also interested in is looking at things like pathway analysis, because the genes or the genetic markers tell us more if we pin them to a pathway and understand the biology of what they may be telling us. We are also looking at Mendelian randomization studies, which are very prominent now across Europe, where we use genetic markers as surrogates of exposure, and they are less subject to bias and confounding, and can tell us more about whether a factor is truly causal or just associated with the outcome. My own interest is in age, both personally and professionally, because age is a surrogate of an important component of cancer, and that is stochastic events. There is a random element to who gets cancer, and we shouldn't forget that. And how do we capture it? And maybe methylation age or biological age is the best opportunity we have for it. So in my short talk, what I hope I've done is remind us all that the environment, your lifestyle strongly affect your risk. In this increasingly omics-based world, people are moving to genetics and epigenetics and forgetting that simple risk factors, smoking, being overweight, etc., are still important targets for public health. We know a lot more now than we did 20 years ago about genetic susceptibility, and we can score this. If we take DNA from saliva, we can score predisposition and look at its interaction with your environment. And finally, I think in terms of translation opportunities, I think risk stratification does offer significant opportunity for evaluating targeted prevention and early detection. And that's what we are focused on in Manchester, and delighted to be joining this consortium to hear about the work going on both across Europe and in China, and happy to take any questions or save it for the discussion at the end. I think there's a lot of work still to be done. Look forward to working with everybody on it. Thank you for your attention.
Thank you, Professor, for your nice talk. So we will discuss later. I'm pleased to welcome Dr. Marc GUNTER for the next talk. Dr. GUNTER is head of nutrition and metabolism section at the International Agency for Research on Cancer from WHO. And he will talk about obesity and cancer. So, Dr. GUNTER, we can see your presentation. It's okay. You can turn on your camera. It's okay. And your micro on and talk. Thank you.
Okay, can you hear me?
Perfectly.
Great, okay. So thank you for this invitation. I was actually in Shanghai exactly 2 years ago, attending a similar symposium. So it's good to see some of the same people. And actually that symposium led to some collaborations that I'm currently involved in with some people from Shanghai. So, so very happy to be here again. So I'm going to be talking about obesity and cancer, and particularly research to try to understand the underlying biological mechanisms linking obesity with cancer using molecular epidemiologic studies. So in this short talk, I'll start by talking about the obesity and cancer in terms of epidemiology and the impact of the obesity epidemic on cancer rates worldwide. I'll then focus on underlying mechanisms and biology, so talking about dysfunctional adipose tissue, what we know currently regarding the link between obesity and cancer in terms of intervening pathways, and then some newer research that we're doing using metabolomics and the microbiome to understand the links between obesity and cancer. And then I'll finish with some important outstanding questions. So the notion that obesity is a potential risk factor for cancer has been around for some time. Actually, the first studies were published back in the mid-1970s. So there's a paper published in November 1975 showing that breast cancer patients tended to have a higher body mass index than the matched controls. And then around a similar period, point in time, Joseph Almini from the National Cancer Institute published the first paper linking obesity with pancreatic and biliary tract cancers. So the idea that obesity is a potential risk factor for a number of different cancers has been around for some time. But in the intervening period, certainly over the last 10 to 15 years, a number of large-scale prospective cohort studies have published their findings, showing that people who tend to be have a higher body mass index or greater waist circumference have a higher future risk of developing a number of different cancers. And a number of different organizations have summarized this data, and this is findings from the IARC handbook on body fatness and cancer, which was published a couple of years ago now, with a summary in the New England Journal of Medicine, which stated that there was sufficient evidence for a potential causal link between higher degree of body fatness and cancer at least 12 different cancer sites. So we can see in this table is that summarizing the different cancers on the left, and then the strength of the association between obesity and that particular cancer. And what's really quite noticeable is that there's quite a degree of variability between different cancers. So you see very strong associations, for example, between obesity and endometrial cancer or cancer of the corpus uteri, and also for esophageal adenocarcinoma. And then for other cancers, for example, colorectal cancer, postmenopausal breast cancer, you see more weaker associations. But given that these are quite common cancers, the popular distributor fraction linking obesity with these cancers actually could be quite high. The IARC handbook also found that there was some suggestive evidence for a link between obesity and a number of other different cancers. So, for example, male breast cancer, fatal prostate cancer, and diffuse large B-cell lymphoma. But at the time, there was insufficient evidence to really classify this as being sufficient. And then there's really inadequate evidence for a number of other different cancer sites. So why is this important? Well, we know that obesity is becoming more prevalent worldwide. We know that there's an ongoing obesity epidemic throughout the world. This is data from the NC Risk Factor collaboration published a couple of years ago now, which looked at mean BMI in practically every country of the world in 1975, in the top panel, and then 2014 in the lower panel. And what it really shows is that the BMI or mean BMI has risen in practically every country of the world, with notable hotspots, for example, North Africa, the Middle East, North America, and parts of Europe. But you can even see some parts of sub-Saharan Africa and parts of Asia have also seen a significant increase in mean BMI in that period. We know that this is contributing to an increase in cancer risk for a number of different cancers, and we recently performed a comparative risk assessment looking at the worldwide burden of cancer attributable to both diabetes and high body mass index. And what we found is that essentially it's likely that around 600,000 cancer cases per year could be attributable to high BMI. And if we combine both high BMI with diabetes, this could be up to at least 800,000 cancer cases. So given the rising prevalence of obesity and diabetes throughout the world, this could be a growing source of cancer cases in the years to come. What's also quite concerning is that the obesity epidemic seems to be also impacting much younger people. So again, this is data from the Institute Risk Factor collaboration looking at mean BMI among 19-year-olds and BMI change between 1985 and 2019. And again, we see that mean BMI has risen among adolescents, again, in practically every country of the world. So even in parts of Africa, Asia, most notably in North America. But just wanted to highlight one hotspot is actually in China, particularly in boys. Mean BMI among adolescents has risen quite considerably in that period. So if obesity is a risk factor for a number of different cancers, and people and obesity is becoming more common among younger people who are then exposed to this risk factor for a longer period of time, again, it could be a growing source of cancer cases in many parts of the world in the years to come. So what can we do about this? So obviously an obvious solution is to implement obesity prevention strategies worldwide. And there is a number of countries that are trying to tackle this, for example, at both at the societal and individual level. So trying to encourage more physical activity, less consumption of calorie-rich foods. And this is having some success in certain countries. But given the scale of the obesity epidemic, I think many of us are somewhat skeptical that this can actually be really impactful on the growing burden of obesity-linked cancer in the years to come. So what's possible is needed is to try to develop more targeted interventions to sever the link between obesity and cancer. And to do this, we really need greater understanding of the biology which lies at the intersection of obesity and cancer. So understanding what are the biological pathways linking obesity, diabetes and metabolic health with cancer, and then using this information firstly possibly to develop targeted interventions, both pharmacologically, maybe also lifestyle, which could be targeted at those who are more likely to benefit. But this information could also be useful for identifying biomarkers of elevated risk for people who have obesity and more poor metabolic health, and then using that for risk stratification. So what do we currently understand as the underlying biological mechanisms linking obesity and cancer? Well, we know that in obesity, there is a dysfunctional adipose tissue, and this is highly metabolically active. We know that in obesity, adipose tissue, there's this increasing inflammatory state where there's infiltration of macrophages and other pro-inflammatory cells. And this leads to this hyperinflamed state, which is often characterized as obesity. And we know that inflammation itself is a hallmark of cancer. So this could be one potential pathway linking obesity with cancer as a direct effect of obesity-induced inflammation. We also know that inflammation can induce insulin resistance in glucose storage tissues, and insulin resistance leads to compensatory hyperinsulinemia. And insulin itself is a growth factor, which I'll come on to in a moment. And there's growing evidence that insulin could be one of the key players linking obesity with cancer. And then finally, we know that in postmenopausal women and also in men, adipose tissue is the main source of estrogens. And estrogens themselves, again, have pro-mitogenic and anti-apoptotic effects. And we know that elevated estrogen is a risk factor for breast and endometrial cancer, with less understood for other cancer sites. But it's also possible that disruption of sex hormone metabolism could also be an important pathway linking obesity with a number of different cancers. So at the mechanistic level, I've already mentioned that insulin is likely to be an important player. We know that insulin itself, in addition to its well-characterized metabolic effects, has properties which could lend itself to being pro-tumorigenic. So what we think is that in the obese state, we have this physiological milieu, which is characterized, for example, by high levels of insulin and free IGF or insulin-like growth factors, as well as pro-inflammatory markers and higher levels of bioavailable estrogens. And what this does is it really engenders this physiological state, which allows cells which bear a cancer-causing mutation to survive. So it's really engendering a pro-proliferative, cell survival environment, which could lead to the promotion of cancer. From an epidemiological perspective, we've been working on trying to understand the link between obesity and cancer through looking at intervening hormones such as insulin and other factors. This is just some data I want to show you around insulin and C-peptide, which is a biomarker of insulin secretion and its association with colorectal cancer, where we've pulled data from 10 prospective cohort studies, which involve around 10,000 incident colorectal cancer cases and 20,000 controls. And what we see is if we can compare individuals in the highest quintile of circulating insulin or C-peptide with those in the lowest quintile, they have a roughly 40% higher risk of developing colorectal cancer over the follow-up period. And this was in a multivariable model adjusted for BMI and other colorectal cancer risk factors, so suggesting that there does seem to be this robust association between circulating insulin or C-peptide with colorectal cancer. Consistent with this, we've also been trying to do work using genetic traits. So Kenneth already mentioned Mendelian randomization and using genetic data to try to understand causal links between cancer risk factors and cancer development. This is work that we're just about to publish from the GEPO Consortium for Colorectal Cancer, which includes 53,000 colorectal cancer cases and 46,000 controls, where we looked at a range of different glycemic traits or genetic instruments or predictors of these different glycemic traits in relation to colorectal cancer. And what you can see, fairly robust evidence that fasting insulin is associated with colorectal cancer. So per 1 standard deviation increase in fasting insulin, we see a 73% increase in colon cancer risk. And this was fairly consistent across different subsites of colorectal cancer, whereas for the other glycemic traits, the results were generally null. So what it suggests is that it's quite likely insulin is a key causal player linking obesity with cancer. So potential interventions which could target insulin might be useful for certainly colorectal cancer prevention. What's also interesting is that we know that obesity is not a homogeneous phenotype, that there does seem to be variability in terms of the metabolic consequences of obesity. So this has really come from much of the cardiovascular and diabetes literature, that we know that there is a subset of people who are obese who do not seem to have the metabolic abnormalities which are typical of obesity, for example, high levels of insulin or triglycerides or inflammation. And these might have been shown not to be at elevated risk for diabetes and cardiovascular disease. So what we did was we investigated this hypothesis for cancer, and we categorized individuals, for women who were involved in Women's Health Initiative and also in the EPIC cohort, into 4 different groups. So those who are metabolically healthy, normal weight, so people who have a normal BMI and have normal insulin levels; metabolically unhealthy, normal weight, so people who are normal weight but have high levels of insulin; and then this metabolically healthy overweight phenotype, so people who are overweight but have normal levels of insulin, and metabolically unhealthy overweight. And what you can really see is, compared to those who are metabolically healthy, normal weight, those who had poor metabolic control had an elevated risk of both breast and colorectal cancer, irrespective of whether they had a high BMI. So you can see that these people who are lean and had have high levels of insulin had an elevated risk of both breast and colorectal cancer, whereas those who are metabolically healthy overweight did not have elevated risk. So this really suggests that it's this metabolic phenotype, which might be characterized by high levels of insulin, seems to be the driver of these cancers. So in addition to insulin, a number of different molecular epidemiologic and experimental studies have evaluated links between obesity and cancer, and as part of the IARC handbook on obesity, we evaluated the mechanistic literature linking obesity with different cancer sites. And what came out of that is really there was really quite robust evidence that certainly insulin and IGF inflammation are likely to play key roles in certainly colorectal, postmenopausal breast cancer and endometrial cancer, and steroid hormones are likely to, we know that they play a key role in postmenopausal breast and endometrial cancer. But certainly for most other cancer sites, there's really a paucity of data linking obesity with these different cancers. And so we need more, certainly molecular epidemiologic data as well as experimental evidence to try to interrogate links between obesity and these other cancers, many of which confer high mortality, such as pancreatic and liver cancer. So what other approaches were available to us to try and probe the obesity cancer link? Well, I think there's a number of different technologies which are now available, which allow us to probe more deeply into the biochemistry linking obesity with cancer. So certainly metabolomics and proteomics, so the ability to measure thousands of metabolites and proteins in a very small single biological sample, I think holds a lot of promise, which can allow us to probe more deeply into the biochemistry and also potentially identify novel pathways and biomarkers linking obesity, metabolic dysfunction, and cancer. And then on the other hand, also there's growing awareness that the microbiota, and particularly the gut microbiome, likely plays an important role. We know that it strongly impacts adiposity and metabolic health, and it's a potentially important modifier of the obesity-cancer relationship. It's also a major source of hormones. So, for example, the gut microbiota produces a lot of estrogen and other potential proteomogenic factors. So this is really an area that it's really been understudied. I think only in the recent decade, there's been growing appreciation that the microbiome plays a key role in normal physiology, but its potential links with cancer are relatively understudied. But again, this could be an important link between obesity and cancer. So I'm just going to give a few examples of some of the work we've been doing to use metabolomics to understand the link between obesity and metabolic dysfunction and cancer. And metabolomics, I think, shows great promise because it really can effectively capture kind of intervening biological pathways linking exposures such as diet, obesity, physical activity, and other risk factors, as well as a microbiota, and allows us to capture this kind of metabolic readout at the intersection of both host genetics as well as the environment, and then we can relate these metabolic or metabolites to cancer risk. So how can this potentially help in cancer research? So firstly, it could potentially perhaps refine the high-risk phenotype. So I already mentioned that there's this metabolic phenotype which seems to be associated with cancer irrespective of body mass index. We don't really understand the causes of that or its full nature. So potentially metabolomics could be useful in trying to understand what is that potentially high-risk phenotype for cancer, to go beyond anthropometric measurements and to define a metabolic signature among obese and potentially lean people associated with cancer development. It can also be useful for identifying novel markers of exposures, as well as identifying novel sets of predictive and potentially prognostic and diagnostic markers, which can be useful for risk stratification. And then importantly, identify important molecular targets and pathways for interventions. So we're involved in coordinating a very large cohort here at IARC, the European Prospective Investigation to Cancer and Nutrition, which is a cohort of more than 520,000 Europeans recruited across 10 different European countries. And these are being followed now for almost 20 years. And at baseline, we collected a blood sample as well as detailed information on diet, lifestyle, and over the years, this has become a really quite an important resource for cancer research. So currently, the last round of follow-up, these are the number of incident cancers across the EPIC cohort. So we have, for example, 15,000 women diagnosed with breast cancer since baseline, more than 8,000 colorectal cancers, more than 6,000, 7,000 lung and prostate cancers. But what's also quite exciting is that we have this growing number of incident cases for less common cancers. So, for example, even cancers which are relatively uncommon in Europeans, so thyroid, liver, ovarian cancer, we have more than 1,000 incident cancers now. So this enables us to potentially investigate the etiology of these less common tumor types. But for the more common cancers, also it enables us to perform very detailed subsite and try incorporate, for example, molecular phenotypes and subtypes, which might allow us to probe more deeply into the link between different risk factors and cancer subtypes. So just to show some results for some of the metabolomics work we've been doing within EPIC, I wanted to show you the results from the breast and endometrial cancer studies, because I think these is quite striking. So these are two cancers which are female hormone sensitive cancers, which share a number of different risk factors, including obesity, a number of different reproductive factors, diabetes. But what you can see is that the kind of metabolic profile associated with the development of breast and endometrial cancer, at least in EPIC, are quite different. So for breast cancer, we have, for example, the odds ratios for association with breast cancer along the bottom, and then the p-value along the y-axis. What you can see is that we saw this cluster of metabolites, all of which had an inverse association with breast cancer. So these women who had higher levels of these metabolites at baseline when they were still healthy had a lower risk of developing breast cancer during a follow-up. And most notably, we saw associations with arginine, which is an amino acid, which certainly endogenous levels have not been linked to breast cancer to date, but there are a number of clinical trials showing that supplementation with exogenous arginine tends to confer a better prognosis among breast cancer patients. And on the other side, we saw very strong positive association with the C2 acylcarnitine, which is a compound which is involved in fatty acid oxidation, has been strongly linked to diabetes and poor metabolic control. So again, this is consistent with there's this kind of link between metabolic dysfunction, diabetes, and breast cancer. On the right-hand panel, this is associations for endometrial cancer, and you see the pattern of metabolites is quite different. So here we see positive associations with some of the branched chain amino acids, so valine, isoleucine, and then quite robust inverse associations with glycine, which again is an amino acid which has been implicated in diabetes and tends to be lower levels among people who have diabetes or obesity. And then this lipid piece, phosphatidylcholine, which again some experimental data suggests can have potential anti-proliferative effects within a number of epithelial tissues, including breast and endometrium. So just wanted to show that this metabolomics type of approach can potentially uncover potential novel and maybe more specific pathways linking metabolic dysfunction with different cancers. My colleague Vivian Villon, he's been working on trying to identify common pathways across different cancers in EPIC using metabolomics and distinct metabolites. And this is data for breast, colorectal, endometrial, hepatocellular carcinoma, and kidney cancer, where the metabolites listed along the bottom, and then green is evidence of an inverse association, which was significant after FDR correction, and then red is a positive association. And what you can see is the pattern across the different cancers is actually quite different. So we see a very large number of metabolites linked to liver cancer, which we kind of expected given the important role the liver plays in metabolism. But we do see some consistency across different cancer sites. So for example, this for kidney, liver cancer, and endometrial cancer, we see this positive association with glutamate, again, which is consistent with experimental data suggesting that glutamate somehow upregulates proliferation within cancer cells. And then a number of inverse associations, so for example, for glycine for endometrial and liver cancer. And then again, some specificity. So for example, for colorectal cancer, we saw this quite strong inverse association with histidine, which is a metabolite which has also been implicated in gut microbial metabolism, so suggesting that potentially this could be a link between the gut microbiota and colorectal cancer risk. We've also been using metabolomics to really investigate the obesity metabolome and try to understand the metabolites which are more strongly linked with obesity and poor metabolic control. So not surprisingly, we see a very large number of metabolites which have significant associations with obesity. For example, some of the branched chain amino acids, valine, glutamate, some of the phosphatidylcholines with very strong associations with high BMI. And then again, some inverse associations. So for example, for glycine, serine metabolites, glutamine, and then some other phosphatidylcholines. And what we can do is then take these obesity metabolomic signatures and try to link these to cancer. And this is what we did for colorectal and endometrial cancer, as we identified an obesity metabolite signature, which includes a number of different metabolites which seem to be differentially modulated in obesity. And we looked at this both using EPIC data as well as data from an intervention study where we had a number of different individuals who lost weight, and we had blood samples pre and post weight loss. And then we took this metabolite signature, which was identified using PLS, and then associated it with both colorectal and endometrial cancer. And what you can see is that this signature seemed to have a positive association for both colorectal and endometrial cancer, although this was weakened following adjustment for the anthropometric measure for colorectal cancer, whereas for endometrial cancer, the association was maintained, so suggesting that this signature is potentially capturing more about the link with obesity and endometrial cancer beyond anthropometric measurements such as waist-hip ratio, or waist circumference, or BMI. So just to conclude, some answers to questions around obesity and cancer. So I think there's still a lot we need to understand around causal biological pathways. So certainly insulin seems to be emerging as a key player linking obesity with cancer. IGF-1, which is a kind of a cousin of insulin, which has a strong mitogenic effects, but more complex relationship with obesity. I think there's still quite a lot of questions around its potential role linking obesity and cancer, as well as inflammation. We know is important, but what specific pathways and what aspects of the immune system are important for cancer development, I think is still understudied. There's relatively little knowledge on differences by subsites and subtypes. So I think as a number of different consortia, for example, have a growing number of data on molecular subtypes of different cancers. I think this will be an interesting area in the future to explore. Other metabolic pathways, so can metabolomics offer anything in terms of novel pathways and markers? Role of the gut hormones, also role of the gut microbiome, I think will be an important emerging area. Does weight loss mitigate risk once someone has already attained obesity? This is actually quite difficult to explore in the absence of randomized clinical trials, but there is some suggestion, at least from some of the observational cohorts, that weight loss, for example, in postmenopausal women reduces risk of breast and postmenopausal and endometrial cancer. Can we go beyond anthropometry to identify more refined metabolic phenotypes which are specific for cancer? And then lastly, just want to stress other population specificity. So much of the research which has been conducted in this area has been done mainly in Europeans and in North America. There's less data from Asia, Africa, and other parts of the world. And we know that there's different types of fat distribution, different metabolic consequences of that in different populations. So I think this is going to be a really interesting area to explore in the future. And this could be an area where we could potentially collaborate with some of the groups in China. So I'll finish there with my acknowledgements and collaborators, and happy to answer questions at the end.
Thank you, Dr. Gunter, for your presentation. I think we will have an interesting discussion at the end between those three first talks. And now I'm pleased to welcome Professor Xian Yongbing from Shanghai Cancer Institute, affiliated to the Medical School of Jiao Tong University. And we will continue to talk about epidemiological studies. So the floor is yours.
Okay. Let me share our. Can you hear me?
Yes, we can hear you, we can see you, and we are about to see your presentation.
Okay.
Perfect.
Thank you. Thank you. I'm Yongbing XIANG from the Shanghai Cancer Institute. First of all, thanks this opportunity for to talk about our study. Okay. Yeah. To talk about our study or research experience during the past centuries. I'm going to talk this topic I listed in these slides. Sorry. What we have done during the past 50 years, but something for what we have now currently doing now, including cancer statistics. Some short review of the case control study we conducted for common cancers, as well as some information for the ongoing population-based cohort studies in our department. Finally, I will show you some finding or research results from our liver cancer study. Yeah. Okay, the first one, let us see the cancer statistic in our city. This is from the annual report of the Shanghai Cancer Registry. The Shanghai Cancer Registry, they published the annual report recently for the cancer statistic. From this annual report, you can see what you have, the cancer burden in the city, which can be stratified by the gender, or also as well as stratified by the urban areas or the rural areas. I listed the number of incident cases for the whole city, including the crude rate and age standardized rate of the whole city, in both in male and females, and also including the urban area or rural areas. If we compare with the figures from the global care from the International Agency for Cancer, from IRC, you can see the age standardized rate of the male, of both for male and females, were higher than the global average rate, from at the same year or the same times. So this is the cancer pattern or cancer burden now in our city. Okay, let us to see the cancer statistics by gender. This is this slide show you for the cancer statistic among males. Of course, the leading cancer site is lung cancer. Following are the colorectal, stomach and prostate cancers. Liver cancer ranked the 5th. And the next is thyroid, pancreas, and urinary system cancers of blood and kidney. Last one is the esophagus. This is the statistic for among males. Again, among females, the first one is still the lung cancer. The second one is and the third one is breast cancer and thyroid cancer. The colorectal cancer is the fourth one. But in male, the colorectal cancer is the second one. But liver cancer ranked the 7th, not the 5th in males. I highlight liver cancer because among the common cancer, liver cancer is the major site as we are interested. So I just highlight the liver cancer among male and females. In China, the Shanghai Cancer Registry was the first one to provide the cancer date to the cancer incidence in 5 counties, CI5, from the volume at early of 1970, last century. So if you want to, you are interested in the time trend of cancer, you can look back to the volume 4 of the CI5 and to see the cancer using the cancer date and to see the time trend of the cancers. If you for any cancer site you are interested. So I think the Shanghai to contributed to the cancer statistic in China as the first one. Okay, we take a quick look for the cancer statistics. This is the timeline for the cancer registry, because as you know, the cancer registry was moved out of our institute to the Shanghai CDC since the early of this century. So most of the case control studies we conducted for especially for the population-based case control study we conducted during the last 2 decades, because I think if you want to design a case control study, especially for the population-based, you need the strong support from the cancer registry. So this is the reason why the case control study we conducted during the last 2 decades, in last century. At that time, the cancer registry was in our department. So this is the history of the Shanghai Cancer Registry in Shanghai. So the case control study we conducted 20 years ago, I think covered almost or the most of the common cancers in Shanghai, both in male and females. I list a lot of many cancer sites in this slide because, but with the exception of the liver cancer. So many risk, or in terms of risk or protective, many factors were identified from our case control study we conducted 20 years ago. It is interesting, as we expected, the dietary intakes of the fruits, vegetables are linked to the reduced risk of common cancers. So you can see for almost the common cancers, the fruits or vegetable intakes are linked to the reduced risk of these common cancers. But for the smoking, alcohol drinking, or as well as the preserved food or the salted food, and so on, are associated with the increase of the common cancers. Yeah, all these findings or results from our population-based case control study 20 years ago. But okay, sorry, I missed the tea drinking and physical activity. The tea drinking, because the dietary patterns are different with that in Western countries. So tea drinking and physical activity will link to the reduced risk for some cancers, also for some cancers. Red meat are especially related to the risk of colon and endometrial cancer. I think, yeah, although this results from the case control study 20 years ago, it is interesting in terms of the epidemiology of public health. It is important to have this interesting finding or research. Okay, the third part is cohort studies, ongoing cohort study we conducted in Shanghai, because the case control study and the cohort study are the 2 popular designs in cancer epidemiology. But the cohort study is so complicated. If we want to design, especially for the population-based cohort study, I mean, it needs more manpower, more funding, and needs a long-term follow-up. So the cohort study is very difficult to conduct. So not like that we conducted the case control study, we conducted many case control studies before, 20 years before. So several prospective cohort studies in our department by my colleagues, conducted by my colleagues, just I think the 4 I listed in this slide, just the 4 prospective cohort studies in our department during past 40 years. Among these cohort studies, the last 2 are still ongoing for the follow-up, including the passive and active follow-up, so-called Shanghai Women's Health Study and the Shanghai Men's Health Study, because the previous 2 cohorts were stopped. For the Shanghai Men's and the Shanghai Women's Health Study, I presented you for the response rate, including the baseline. I'm sorry, this is for the baseline response rate, and including the response rate for each active follow-up. So I think we satisfy for the response rate, both for the baseline and each active follow-up. Within this cohort, the baseline survey for the women's cohort is about the time. Baseline survey time is 20 years ago. For the men's health study, the baseline survey is about 50 years ago. These two cohorts are still ongoing for follow-up. The follow-up way we used the combination ways to follow up the cohort members, so-called the passive and follow-up. Active follow-up. Active follow-up is the major way, one of the major active follow-up ways, the home visit. The passive follow-up is we conducted the annual record linkage with the Shanghai Cancer Registry and the Shanghai Wider Statistic to identify the outcomes, including cancer or other chronic diseases we are interested. This is the passive follow-up for these two cohort studies. If you are interested for the study design of the cohort, you can check the profiles from these two publications. I think the one is in American Journal of Epidemiology, another is in International Epidemiology, International Journal of Epidemiology. You can check the detail more about the study design of the two cohorts. Within these two cohorts, we also conducted validation study for the food frequency questionnaires used in the male or female cohort, as well as the validation study of physical activity questionnaires. Because I think you know, if you conduct or design a cohort study, this is one of the important steps to finish for the cohort study. Except for the FFQ or the PIQ, if you use another new questionnaire to collect some of the information, you may do the same way for the validation studies for the cohort studies, for the parent cohort studies. Okay, yeah, next slide will show you the response rate or some basic information for the male and female cohort. This is the baseline and each active follow-up of the response rate. I think the response rate is very well. We satisfy for the response rate from each active follow-up. For the female cohort, the 5 active follow-ups were finished up to I think to the end of 2018. The response rate is still very high. Also, we are happy we also are happy to have the high response rate of the female cohort as well. Like the cancer statistic or cancer patterns, as I show you for the whole city of the Shanghai, yeah. In male cohort, we can count it because we obtain or many cancer cases identified from the cohort through the active or passive follow-up. So at least the top 10 cancer sites. This is in the male cohort, not for the whole pattern of the whole city, but I think this is similar with that of the whole city. Among males, the first one is the lung cancer. The first leading cancer site is lung cancer, and the second one is the stomach, and the third one is the colon cancer. But if we combine the colon cancer and the rectal cancer, I think the colorectal cancer will be ranked the second one. So this is the same with the whole pictures of the whole city, the cancer pattern among males. liver cancer is our major one to be interested. So as the same orders, liver cancer ranked the 5th in our male cohort. For the women's cohort, I think the pattern is a little bit different with that I show you from the whole city. Yeah, the breast cancer is the first one. The lung cancer is the second one. But for the whole city, among females, lung cancer is the first one. So liver cancer, now the liver cancer is the 9th one. For the whole city, liver cancer is the 7th one. So I think, yeah, maybe one of the reasons may be the age groups of our female cohort members, the age from 40 to 70 years. I think maybe the one of the reasons the age group. Finally, using the resources or database from our 2 cohort studies, I think if you set up our cohort studies, you can use the resources or database to conduct many studies for common cancers. As I said before, yeah, the liver cancer is the cancer site as we are interested. So we use the resources of the 2 ongoing cohort, so-called Shanghai Men's and Shanghai Women's Health Study. We do many studies within this cohort using the 4 cohort date or conducted a nested case control study within the cohort to see which potential the risk or protective factors for liver cancer. Because as you know, the liver cancer in China, there are a lot of uncertainties for the risk factors, which need to be investigated or evaluated. So just as an example, I will show you some results or findings listed in this slide, because the liver cancer project of our liver cancer project is a comprehensive program. So I just show you some example of all the studies or of our studies. First one is we want to test to assess the association between diet and vitamin intakes and liver cancer. This is the simple protocol of our study. The closing date, the closing date of the study is the end of 2009, about 10 years ago. So using the data from men's and women's health studies, of course, the outcome is the liver cancer. Use the Cox regression model to adjust all potential confounding factors to estimate the relative risk, adjusted relative risk of the diet or vitamin to see whether are associated with the risk of liver cancer, both in men and both in males and females. The first one is we are interested in the dietary vitamin intake and the liver cancer risk. We want to see the association between, because the follow-up time is no longer. So just 267 cohort members who diagnosed with the liver cancer. I mean the incidence cases from the 2 ongoing studies. The results suggested the dietary intake of vitamin E may reduce the risk of the liver cancer. The second one, using the same database, we conducted a study to test the dietary patterns association with, which may be associated with the lung cancer risk. Of course, the first level, we constructed the dietary patterns using our FFQ, the food frequency questionnaire. We constructed the 3 dietary patterns, so-called the vegetable-based dietary pattern, food-based dietary pattern, and meat-based dietary pattern. Among these 3 patterns, we just found the vegetable-based dietary pattern was linked to the reduced of liver cancer, especially in males cohort. So this is the main result, the adjusted hazard ratio for, yeah. The third example, we want to test the relationship between the type 2 diabetes and liver cancer using the same the same protocol using the data from our 2 the cohorts. The exposure is type 2 diabetes. Outcome is the liver cancer incidence. The closing date of the study is the same at the end of 2009. So in our study we try to do a lot of statistic analysis, including subgroup and sensitivity analysis to see the results are robust. So I think the protocol is the same with the previous 2 studies. Because we used the same, so the number of the cases is the same, and adjusted after confounding, the adjusted relative risk is about 1.6, both in male and females. Suggested the type 2 diabetes was significantly associated with the increased risk in Shanghai, in China. Last one is the study to investigate obesity and female liver cancer. I think the protocol is the similar one, but the closing date is up to the 2016. So we have a longer follow-up time. So this is different with the previous 3 studies. So we have a more female liver cancer incident cases, 241 cases up to the end of 2016. So even because the follow-up is longer than the previous 3 studies. Of course, the obesity was linked to the increased risk of female lung cancer. The increased risk of female lung cancer are about by 30% to 40%. We also observed a linear relationship between obesity and female liver cancer, but not for the long linear relationship. Okay, I think, yeah, I'm not, the time is running, so hopefully I wish to show you the whole pictures of our research experience or studies during the past 50 years, including cancer statistic, as well as some information of the cancer registry. Very short review of or summary the results from the case control study we conducted 20 years ago. And I would like to show you some information for the design or basic information of the 2 ongoing cohort studies. so-called Shanghai Men's and Shanghai Women's Health Studies. This is the, I think, using the resources or database we can conducted many studies for common cancers. So because the liver cancer is the cancer scientists we are interested. So we just show you some findings or the results from our liver cancer study, because the liver cancer study is a comprehensive program to evaluate or investigate all potential risk factors which may be linked to the liver cancer in China. So I think this topic will wish to give you the whole pictures of our studies or the studies conducted by our colleagues during the past 50 years. Okay, so I would like to thank staff research or students in our department and my colleagues from the incidents from the University Institute, especially from the International Institute for Research on Cancer. I appreciate for their great support for our study, as well as thanks for the grant or the funding support from Shanghai or the central government, Chinese government, and the funding from the National Cancer Institute of the United States. Okay, that's all. Thanks for your attention. Thanks for your time.
Thank you, Professor. Thank you for the presentation of all those studies. We'll get back later to any question about it. So I'm pleased to welcome Professor Gareth EVANS, who is Professor of Medical Genetics and Cancer at Epidemiology, Cancer Epidemiology, sorry, at the University of Manchester, and who is also consultant in medical genetics and cancer epidemiology at Central Manchester Hospitals, NHS Foundation Trust, and the Christie NHS Foundation Trust. So we will hear talk about population risk stratification, especially for prevention. So we can see the presentation. Is your camera on? It's okay. And we can hear you.
Yes, thank you very much, Marlene. Thank you very much for the introduction. So I'm going to talk about how we can really very accurately risk stratify populations now, and then target more frequent and earlier screening and also preventive measures on those at the highest levels of risk. And I'm going to base this largely on our predicting the risk of cancer at screening study, which recruited women aged 46 to 73 between 2009 and 2014. And we currently have over 1,600 breast cancers, incident breast cancers, and 621 breast cancers in those that have a DNA sample, with over 10,000 with a DNA sample. So this slide was produced a few years, about 18 years ago, looking at the sort of non-family history risk factors. And clearly, the biggest measurable risk factor is breast density. And a lot of work has been done in the last few years to identify that. And there's a six-fold risk between those with the lowest level of density and those with completely dense breasts. So a really, really big risk factor. Not only is it a risk factor for future breast cancer, but also it masks potential breast cancers, and therefore you need to think about other modalities for screening. There are many classical risk factors which are measured in a number of risk models, including the thyroacutic model, which we've used in this study. Age at starting periods, number of pregnancies, particularly the age at first full-term birth, younger age is protective, age at menopause, HRT use, BMI you've already heard about. It's a bit more complex than just the BMI, which I will probably discuss in the discussion. Alcohol intake, a small risk factor, and also exercise. Family history is obviously a long-established risk factor, and we know that in the extreme situation with inheritance of faults in the BRCA1 and BRCA2 genes, the risk can be extremely high, up to 80 to 90%. So the number of family members and the ages at which they're affected clearly affect risk. But we now know that probably the majority of the inherited component of breast cancer, and breast cancer has about a 27% heritable component, is actually due to polygenic inheritance, mostly of common genetic variants of low effect size. And there are now over 300 of these that have met genome-wide significance and been validated, but there are probably over 1,000 that are just sub-genome-wide significance. So in terms of breast density, it is a heritable risk factor, and we need to bear that in mind when using SNPs, many of which also predict density to some extent. There are many different measures of measuring this. Automatic measures are obviously the best way forward, but these actually miss quite a few important issues that are seen by radiologists, and we used a visual assessment score as the main measure, and this was superior to Volpara, an automatic measure. Artificial intelligence appears to be bridging that gap and may be able to take into account actual features in the breast which could represent early cancers. So if you were to have two 40-year-old women, whereas on the left with this entirely dense breast, and on the right, this breast with virtually no density, the difference in risk between these two women would actually be around a 4% lifetime risk in the UK compared to a 25% lifetime risk. So really striking differences. And you're looking at about 10% of the population being in each of these two categories. So in reality, breast cancer risk is not simply the lifetime risk for that country, which in the UK is possibly as high as 1 in 8, or an 80% risk if you carry a fault in BRCA1, BRCA2, or P53, but it's actually a huge distribution which has its extremes in those with BRCA1 and 2, but at the other end, there may be a significant number of women who actually have risks of maybe as little as 1 in 50 of developing breast cancer in their lifetime. Obviously, the idea is at the higher levels of risk, we can target preventive strategies such as chemo prevention, MRI screening, which is obviously much more expensive than standard mammography, but is highly sensitive, and also risk-reducing surgery for those that want to move down that pathway. So, of course, it's a myth that risk stratification doesn't occur at all. It does occur when women self-identify with a family history, and there is screening in our national screening program in the UK for the very high risk. This currently represents less than 1 in 1,000 women, but nonetheless, those who are proven carriers in the high-risk genes get annual MRI screening between 30 and 50, and annual X-ray mammography from 50 to 69. There is also NICE guidance, which means that up to about 3% of the population that self-identify will get access to additional screening annually as opposed to 3 yearly from 50 with X-ray mammography from 40 to 59 in the high risk group and 40 to 49 only in the moderate risk group. So when it comes to the single nucleotide polymorphisms, there are many of these now, and I'm going to give you a sort of slow history of how adding in more has improved our ability to risk stratify. The first SNPs were identified in a genome-wide association study in 2007, and these have gradually increased. Obviously, the first 18 that were identified had the largest effect sizes, so each incremental addition actually adds very little extra amount to what the polygenic risk score can do, but the number of SNPs actually means that you do get substantial changes. So the way we have used the SNPs is that we normalize the risk around one. You get 3 possibilities. You get 2 wild type copies of the so-called normal allele. You get one of the risk allele or the allele which is not the normal allele, and then 2 of the risk or non-normal allele, and then you multiply these risks together to get a polygenic risk score. And we've initially used this PROCAS population with a subgroup looking at the DNA, and we've genotyped in various stages, the first 18 SNPs, and then using an OncoArray, we've used the up to 313 SNPs in the current analysis. With mammographic density, we've used visual assessment score, as I said, that was superior to Volpara, and initially we compared this in 2 risk models, Gale and Tyrer-Cuzick. And looking at the initial study published about 6 years ago, we had 697 women diagnosed with breast cancer after recruitment. This was at an early stage in the follow-up, but we showed that actually breast density was more accurate than looking at all of the other risk factors put together, produced the highest interquartile odds ratio of 1.48 compared to only 1.36 for Tyrer-Cuzick, and even lower for the Gale model at 1.22. And it added additional information to the Tyrer-Cuzick model, allowing you to calculate 10-year risks. Now, adding in the genetics, as I said, this has been done in a number of stages, 10,000 women with DNA samples, 553 already had breast cancer. So we've concentrated on the prediction after. So 621 have developed breast cancer and had SNP18. And then an OncoArray has been carried out on all of those 621. And we've done SNP 313 and a gene panel on 340. And these are the number of controls, about 3 controls per case, which were matched on age and time of mammogram. And these are the first 18 SNPs, just to show you that some of the effect sizes here are quite large. FGFR2 and TOX3 have the largest effect size. You can see here that the minor allele is actually protective, and that's why you get an odds ratio below 1. So looking at SNP18 in the first instance, this is the sort of spread of risks by just using standard risk factors in Tyrer-Cuzick. You can see that these are women of screening age 46 to 73, that more than 50% are in this average risk group, 2 to 3.5% 10-year risk, with pretty much no women down below 1%. When you either add in the mammographic density or the SNPs, you can see that you're starting to push more women into the extremes here, and that SNP18 is about equivalent to mammographic density. But when you put all 3 together, you really start to spread out the risk. And here only 35% of women now are in the the average risk category, with much more being spread out beyond that. Now, initially, when we looked at SNP18, there was almost no overlap between SNP18 and the density residual, or SNP18 and the tyrocusic 10-year risk. So we were able to add this in unadjusted. It also showed an incredibly good risk calibration. You can see here, the black line here almost completely overlaps with the dotted line where it should. So it means it is not over predicting at the top end. It's not under predicting at the bottom end. And this shows you the discrimination between cases and cancers. You can see those at moderate and high risk, above 5% 10-year risk. You can see we're identifying about 18% of women in the control group, but about 30% of the cancers. And at the bottom end, about 30% of the cancers in the below average group, only getting about 17% of the cancers. So you're really starting to be able to risk stratify. Now, we predicted, this was in 2014, that adding in more SNPs would mean that you could push this out further. This was based on 67 SNPs. And indeed, our further work has shown that. And this involved actually carrying out the Illumina OncoArray and being able to use the validated SNPs. So initially, we looked at SNP 143. The SNP 313 includes imputed SNPs rather than actual real SNPs in inverted commas. And what we showed, and this was published last year, is that the score really was extremely good. It wasn't quite as well calibrated as SNP18, but accuracy was retained after adjustment. You can see here the really good unadjusted 1.93 interquartile odds ratio. And it was also predicted both for ER-positive breast cancers at 1.94 and ER-negative breast cancers at 1.7. And so looking at this overall, you can see that, that we can now identify at moderate and high risk about 20% of the population at TC8 plus who develop 43% of the breast cancers and 48% of the stage 2 breast cancers. So a fifth of the population is almost identifying half of all of the stage 2 cancers. And at the bottom end, so women with less than the 10-year risk of a 40-year-old, less than 1.4% 10-year risk, we're able to identify about 1 in 6 women who only develop about 5.5% of the stage 2 cancers. And this just shows you, taking out the cancers, the spread you now get with here about 12% in the moderate risk group, about 9% in the high risk group here compared to tyrocusic, which essentially really doesn't identify people at the low end and far fewer at the high end. And this is what actually happens in our NHS breast screening program, apart from the 1 in 1,000 who are in the very high risk. Essentially, everyone is treated the same. Everyone gets 3 yearly screening. So is it predictive? Now, we only have good prospective data in those that had SNP18 because everyone has been genotyped. And you can see here that using the combined assessment, tyrocusic density and SNP18, these are accurately predicting in the ranges that they're supposed to predict. So 12% in the 8% plus, just under 6% in the 5 to 7.9% moderate risk. And in the low risk, you can see this is comfortably below 2%. Importantly, also, I've already shown you that you're getting more stage 2 cancers in the high risk group, but also what we're seeing is cancers that are potentially overdiagnoses in the low risk group. So more of them had grade 1s statistically significantly in the low risk group, and more of them had extremely good prognosis breast cancers, that is low grade and moderate grade DCIS. So over 50% in total had really, really good cancers in terms of overall prognosis. You can see here the increase in numbers from tyrocusic to tyrocusic and density, tyrocusic density and SNP18, and then SNP143, increasing numbers identified in these groups by including more in your risk stratification. And the same thing occurs in the high risk group, getting more and more people into the high risk group, and of course more cancers. And importantly, you do not lose the odds ratio between cases and controls. Here it's increasing the risk in this group to 2.3-fold comparing cases and controls. So what about adding a gene panel, the sort of kitchen sink, throwing it in this situation? Obviously, for someone who carries a mutation, it's a very big deal. But the question is, how much does it actually add to population stratification? So we're able to do this on 340 cases. And we were only able to identify an actionable gene in 19 out of 525 women with breast cancer. That's 5.7%. And only 1.7% had a mutation in BRCA1 or BRCA2. When we looked at the controls, only 1.3% had an actionable breast cancer gene, and only 0.56% had a pathogenic variant in BRCA1 or 2. So a really small proportion of the population. And this is the Manchester score, which predicts breast cancer. You can see Manchester score of 15 or higher would be those that would qualify for testing. You can see the majority of these would not have qualified for clinical testing. But when we look at the actual risk these women were in before the gene panel was done, you can see here that actually the majority of the carriers were already in the moderate or high risk group. 10 of the BRCA1 and 2 carriers were in that high risk group. You can see here the genes that, 10 of those with actionable genes were already in the high or moderate risk group. So overall, what is this doing? Well, the panel you can see really doesn't add very much. This is the low risk, below 1.4%. You can see a slight improvement because you get a little bit of a downward adjustment for a negative test, but really not much compared to this massive change by adding in lots more SNPs. And then at the high end, again, very little change in the number of cancers or cases identified or controls identified. But again, you can see here this good odds ratio being maintained in this group. In fact, SNP 143 actually ended up with the highest AUC on the basis of that. So this is where we are now, and what we have done now is in a prospective cohort in BC Predict of 2,500 women, 250 with SNP 143. We have had problems with COVID, obviously, in recruitment, but we've given results of their risks within 6 weeks of screening. You can see here the number at high and moderate risk is a bit higher, maybe a bit of self-selection there, 23%. But importantly, a high proportion of the women at high risk have opted for a risk appointment, and really high uptake of both chemoprevention, either with anastrozole or tamoxifen, at 77.5% of those that come, and nearly 80% have opted for the extra additional screening. So this is showing that this can be actually applied in real time in a screening program within 6 weeks of having their mammogram. So what I hope I've been able to show you is that breast cancer risk stratified screening is ready for implementation, that SNPs are far more useful than extended panels, and that risk feedback has already been given now to more than 12,000 women based on polygenic risk scores in Manchester. I'd like to thank our fantastic team. You can see here many of the radiologists who reported on so many visual assessment scores. Thank you very much.
Thank you for your presentation. Hope we can discuss later about your project and studies. So we can move on to Dr. Johanna LEPEULE. I'm pleased to welcome her. She's an environmental epidemiologist and a researcher at the National Institute of Medical Research, and actually at the Institute of Advanced Bioscience. So she will talk about in utero exposure and epigenetics. We can see your presentation. You can turn on your camera and your microphone.
Okay, can you see my presentation in full screen?
Perfectly.
Okay,
Perfectly.
thank you very much. Thanks. So I would like to first thank the organizer for inviting me to present the work we are doing in my team. So I'm going to take a slightly different angle of view compared to the previous presentation, as I'm going to focus on early life and environmental exposure. So my work is not directly targeting cancer, but I believe there are bridges that we can build between the field of environmental epidemiology and the field of childhood cancer. And I think the results we have on the effect of environmental contaminants on the placenta might be of interest for childhood cancer comprehension. Sorry. So there is an increasing number of adult and childhood diseases for which the evidence points to fetal origin, which is a period of vulnerability with rapid organ development. And there are several factors and environmental exposures in the broad definition that have been identified to affect the fetus and increase the risk of many chronic diseases, including metabolic and cardiovascular diseases, but also respiratory diseases, neurodevelopment of the child, and sometimes also cancer during both childhood and adulthood. So this is the concept of the DOHAD, or developmental origins of health and diseases. And the reason of this strong focus on early life is that there are windows of sensitivity, as I said, but there is also windows of opportunity for prevention and intervention. And of course, as early, the earlier we intervene, the earlier we make this action of prevention, and the bigger impact they will have in terms of public health on the population. So, as I said, there are several environmental exposures during early development that have been associated with pregnancy outcomes, such as low birth weight or preterm birth, but also adverse outcomes during development, including asthma or neurodevelopmental disorders, and sometimes childhood cancer. My work mainly focuses on widespread environmental exposures, including, for example, air pollution and temperature and greenness, but also exposure to maternal smoking during pregnancy or endocrine disruptors. Regarding childhood cancer, there is fewer evidence of associations for these environmental factors, part of study design difficulties, but today we can say that there is an increasing evidence of association between traffic or air pollution exposure and childhood cancer, and in particular with acute lymphoblastic leukemia and acute myeloid leukemia. Although, of course, the evidence remains pretty scarce compared to other outcomes that are not cancer outcomes. And there is also some evidence that parental smoking during pregnancy can increase the risk of childhood cancer, especially the central nervous system tumors. Also, although the evidence remain a bit scarce also in this area. And there is also a link that have been quite widely reported between birth weight, with an increased birth weight that would be associated with an increased risk of cancer in childhood. And last but not least, air pollution and in particular particulate matter and tobacco smoking are carcinogenic to humans and classified in the first group by IARC. So the more general question we can ask is how this early exposure could have such very long-term effect during childhood and sometimes also during adulthood. And one hypothesis that might reunite our fields of research and might be of interest for the audience today is the role of the placenta, and more specifically epigenetic marks of the placenta, because cancer development can be initiated very early. So the placenta plays a key role in fetal programming. It supports both the health of the mother and the development of the fetus. And in terms of environmental exposure, this is a pretty interesting tissue because it might provide some records of the exposures occurring during pregnancy. Unfortunately, there are very, very few studies, at least in the environmental epigenetics, that focus on the placenta. So the reason we are interested in epigenetic marks, so especially in the placenta, is because these epigenetic marks, and in particular DNA methylation, are modifiable and can be also persistent even in the absence of the cause that established this DNA methylation modification. So today I'm going to focus mainly on exposure to air pollution, maternal smoking, and phenol during pregnancy. So our study focused on DNA methylation, as I said, in the placenta. This is one of the most well-known epigenetic mechanism, and this is also the one for which we have reliable techniques and that we can use in our existing DNA collection, because the DNA collection we are using were established in the early 20s, in 2003. And this the DNA methylation is also more stable compared to histone modification, and it's a bit less cell and tissue specific. So in our work, for now, we are focusing on data from the EDEN mother-child cohort, which is a cohort including 2,000 women that were recruited in between 2003 and 2006. In two cities in France, Poitiers here, and Nancy in the northeast part. The mothers have been followed up for during the pregnancy, and also the offspring after birth during more than 10 years. And we collected many data, and they also had some clinical examination at different ages. And regarding placenta methylation, so we collected some placenta samples from the fetal side after delivery. We froze this sample and used them a few years ago to measure DNA methylation using the 450K bit chip. This works, we for now focus on 668 samples, which correspond to 668 women. The average birth weight was around 3 kilograms and 300 grams. we had 72% of male and 43% of women from Poitiers and 57% from Nancy. In terms of statistical analysis, we adjusted for the center of recruitment, for the age and the education of the mother, the BMI before the pregnancy, the parity, the season of conception, and some technical factors that are related to the methylation measurements. For some of the environmental exposure that we investigated, we also adjusted for cell heterogeneity and maternal smoking. And the way we analyze the data is that we first conducted epigenome-wide association study for each probe using a robust linear regression with correction for false discovery rate. And we then looked at differentially methylated regions, which are regions that are enriched for probes with a low p-value. So in terms of the air pollution and the link between air pollution and placental methylation, so we first assessed the exposure to air pollution, so using the home address of the woman during pregnancy, and using a dispersion model. So we were able to assess the exposure to nitrogen dioxide, which is the main source of nitrogen dioxide is from traffic. And also we estimated the exposure to particulate matter less than 10 microns, so PM10. So the sources of PM10 are mainly heating, human heating, traffic, and agriculture. And once we had this exposure, so we related this environmental exposure to the placental methylation level. And what we found is globally that there was a significant association between nitrogen dioxide exposure during pregnancy and methylation of genes that were related in other studies related to hypoxia and preeclampsia. And among these genes, the one for which we had the most interesting results was ADARA2B, as you can see here. So among 19 probes on this gene, we show that 16 of them were negatively associated with NO2 exposure, which means that for women who were most exposed to NO2 exposure, the methylation level on these CPGs were lower. And this result was, as I said, particularly interesting because there was previous studies which showed association between hypoxia and preeclampsia and this gene. And there is a really growing literature showing that preeclampsia is associated with air pollution exposure during pregnancy, and that air pollution would increase the risk of preeclampsia. And there is also some studies that showed association between activation of ADARA2B signaling and the pathogenesis of preeclampsia and also fetal growth restriction. So we can see that altogether there are different points and elements that help us to understand what's going on in these different relationships. There is still an open question here regarding the links between methylation of ADARA2B and preeclampsia or blood pressure, which is something that we are currently investigating. And in terms of smoking exposure now, still in this Eden cohort, in the same sample, we had 3 groups of women. So we had women who smoked before and during the pregnancy. We had 70 women who declared stopping smoking before getting pregnant in the 3 months before. And we also had women who did not smoke before and during the pregnancy. And comparing the 3 groups of women, we found that 152 regions were differentially methylated, but only in current smokers. We did not found this differential methylation level in former smokers, which suggests that these regions would be reversibly affected. If the woman stops smoking, these changes in methylation are not found. And we also identified 26 regions for which the difference were present in both in former smokers and in current smoker, which suggests that there is a persistence of these changes even if the woman stops smoking, and suggests that there might be an epigenetic memory of this exposure to tobacco smoking even before the pregnancy starts. Still focusing on maternal smoking during pregnancy, another interesting results is when we compared the 344 differentially methylated regions that we identified in our study to randomly selected regions, a bit more than 800. We found that the differentially methylated regions associated with smoking were enriched in enhancer histone marks, and that transcription starting sites were less represented in this 344 DMR compared to the randomly selected regions. And the last very interesting results from this data was regarding imprinted genes, because these DMR were enriched for imprinted genes, and especially H19 and NNAT and PEG10. So altogether, this result might suggest some mechanisms by which maternal smoking during pregnancy could affect the fetal growth and the later development of the child, including maybe a childhood cancer. And the last association we looked at is with phenol exposure during pregnancy. So the exposure was estimated using urine sample collected at mid-pregnancy. And we looked at different phenols, including bisphenol A, triclosan, parabens, benzophenone 3, and dichlorophenols. And for this study, we focused only on boys, on 200 boys, because we only have phenol exposure for boys in the Eden cohort. And what we found here is that the phenol for which we had the highest number and the more evidence of association was triclosan, with more than 100 differentially methylated region, and especially with DMR that were really large, with more than 5 probes. And for this DMR with more than 5 probes, again, here there was an enrichment in imprinted genes. There were also some genes that were related to cell signaling, cell adhesion, tumor suppression, tumorigenesis, and transcription factors. And there were also some other genes whose epigenetic profile might serve as biomarker of risk to developing cancer. So these results were published recently in Environmental Pollution. So altogether, the results and the preferential targets that we identified for this environmental exposure during pregnancy suggest some mechanisms by which environmental contaminants during early life could affect the fetus and the future child, and especially for air pollution, as we've seen. This might suggest some mechanisms related to preeclampsia. And interestingly, for smoking, we make the hypothesis that there might be an epigenetic memory of exposure to tobacco smoke before pregnancy. And those are crucial information in terms of public health regarding the potential long-term effect that might have smoking in women and in their child. So until now, we mainly focused on this part of the figure, so the association between this environmental exposure and the methylation marks in the placenta, but we are also now focusing more on this part of the graph, which aims at identifying the association between development of the development of the child and the health of the child, with this DNA methylation marks in the placenta, and also because we're going to have more data in terms of placenta samples, which will allow us to increase the power of our studies. So altogether, these kind of studies are of course useful because they can identify some biomarker of exposure or some biomarker of disease. They can also suggest some mechanisms or mediator of the association between this early exposure and later development of the child. But I do think there are also some links to be drawn between this environmental epidemiology field and the childhood cancer field, because here we identified some genes or some CPGs that are associated with environmental exposure. But if of course we don't have the power to look at the association between DNA methylation in placenta and cancer in childhood, because we don't have very large cohorts. But if some people have these very large cancer cohorts and are able to have placenta sampled, there are some very interesting overlaps to identify, I think. So I would like to thank all my collaborators, both at INSERM and in other teams in France and abroad. Thank you very much.
Thank you, Dr. LEPEULE, for your presentation. Thank you all for your presentation. It's time for question and answer session. In order to start the exchanges, I invite every speaker to turn their cameras on. We have seen many interesting epidemiological studies focusing on cancer. We heard about different risk factors and pathways with various analysis angles from genetic to environmental aspects and epigenetic as well. Some of you focused on similar factors or cancer types, so there may be several subjects to discuss. You can either directly ask your question or write them on the chat so I can read them. So is there any question to start with? Professor Evans?
I was going to ask Marc about the link between obesity and breast cancer, because as I mentioned in my talk, it's much more complex than just simply BMI, and it looks like the biggest issue is weight gain, and that actually women who are obese age 20 are strongly protected, not just premenopausally but postmenopausally, from developing breast cancer, and that it's those that gain more than 30% of their body weight between age 20 and the menopause actually double their postmenopausal risks. So the effect of obesity, it can be far greater, and I think the problem is just using BMI is a very blunt instrument, and I guess the question is, why is being obese age 20 actually trumping all of these other issues that were mentioned, such as inflammation, extra estrogen, etc.? So I don't know if you've got some answers for that, Marc.
Yeah, it's a great question, and no, I don't know the answers to all that. But no, I mean, it's quite puzzling why being overweight in younger period of life is protective against breast cancer. I mean, it's been a question that's been people have been trying to figure out for some time. I mean, yeah, I think what it shows, and I tried to allude to this in my presentation, is that yeah, BMI is a very blunt instrument, and we need to try to move beyond that, because as you also saw in some of the work I showed, that there are people who would be classified as being overweight by BMI, but they're not at elevated risk of breast cancer, whereas there's actually lean women who are at elevated risk if you look at their kind of metabolic factors. So I think it's a really important area. We need to try to move beyond just using BMI as a way of classifying risk, and identify maybe a more precise measure, which could be captured, for example, using hormone levels or metabolic health. But the underlying etiology, why being overweight young women is protective, I don't think we fully understand that. I mean, there's been some hypotheses around ovarian cycling and
lower progesterone levels.
Yeah,
maybe. Yeah.
Yeah, no, it's a great question. I think also that this is where studying other populations could be really interesting, because we know that, for example, a woman in China and a woman in the UK who might be classified as having very similar BMI might have very different metabolic profiles because they've got very different types of fat distribution. They have different genetics and different environmental exposures. And there was a very nice study actually showing that Chinese women who moved to the United States, comparing Chinese women in the United States and Chinese women in China, those who have got exactly the same BMI, the Chinese women living in the United States had higher levels of estrogen. And that they couldn't account for that with any other factors in the model. So there's something about living in the West, or maybe it's diet, or
the diet.
Something.
What's in the diet? Maybe
exactly, or maybe it's environmental pollutants. I mean, some of the work that
environmental,
presented, some endocrine disruptors. I mean, I think it's a really interesting area, but yeah, it's a good question.
Thanks.
I guess I have a question. I'm sorry, for Gareth. I mean, some of the work that he
go for it.
Okay. Yeah, I mean, what's your opinion on adding, for example, BMI into some of these risk prediction models for breast cancer? Because I mean, as you showed, it's quite complicated. And
yeah, so I'm actually we're in communication with Jack Cusick to try and get him to alter in the next version, which will be version 9, so that it includes so all of the risk models include BMI. They include height, because height's a predictor, but they also include BMI. And so really we're suggesting now that you need weight aged 18 or 20, and there needs to be a calculation of weight gain as the biggest issue, but also that you need to add in a protection for those that are particularly those that are obese, but even those at the higher levels of being overweight at age 18 or 20 as a protective factor. So that is going to be done. I don't know whether it's going to go into any of the other risk models, but clearly it is a much better way of assessing risk relating to weight.
Yeah, okay, that's great.
Is there any other question?
Hi, this is Tong from Regional Hospital. I don't have a question, but I do have a comment. So we do have another concurrent session going on at the Regional Hospital for the continued education training right now. And online, we have dozens of participants listening to your wonderful talk. So I just really want to express my gratitude for your great talk this afternoon. So maybe you see only 18 or whatever numbers on the for the participants on the Zoom, but I can assure you that there are a lot more, about 100 people online that are watching you guys. Thank you again for your wonderful talk.
Thank you.
Thank you. Is there any other comments or question? No? So maybe we should conclude for this first session. Thank you for our speakers. I hope that you will have the opportunity to exchange later if you have found a common interest for your research programs. And I'll see you tomorrow for the next session of this webinar. Have a nice day. Have a nice evening in China.
Merci bien.
Thank
Au revoir.
Thank you.
Au revoir.
Thank you. Bye.